Hello everyone, this is Dr. Hopkins with our next video. And we're going to build on what we talked about last time in terms of orbitals. We're going to assign, so those are orbitals where one electron will be. Now we're going to assign electron configurations for an entire atom itself. So however many electrons it has, which orbitals are they in? All right, so electronic structure, the first two kind of points we've already learned. We know that each electron only has four quantum numbers, and they are all different. Okay, so that has consequences that we end up with 2 electrons per orbital. We end up with 1s orbital, 3p orbitals, 5d orbitals, 7f orbitals. That means we can have 2s electrons, and then 6p electrons, and then up to 10d electrons, and up to 14f electrons, and so forth. So all of that kind of periodic building up of the table. But we need to know which orbitals are going to be higher and lower in energy to know which ones are actually filled when we're filling in the electrons that we have. So higher N, right? So farther away from the nucleus are higher energy. Higher L tend to be higher energy as well. So the closer they are to the nucleus, the lower energy they are. And so that means that N equals 1 is our lowest. It only has one L, so 1s is definitely the lowest energy orbital. And if we're looking at filling an electron or filling electrons in an atom in orbitals, 1s is the lowest energy orbital to put it into, and so forth. So then we go up to n equals 2, so 2s, well, it turns out we have two sets of orbitals, and the n equals 2. Here's where this L comes in, so the s is lower in energy than the L because L equals 1 is higher than L equals 0. Okay, and the same thing we have with N equals 3. We have 3 of them where we have the 3s, L equals 0, L equals 1, and L equals 2 is the highest of those. But then it turns out that 4s is actually lower in energy than the 3d. Okay, and we get quite a bit of this as we go up the sets of orbitals themselves. So rather than in your book, in most textbooks, they'll have this kind of sideways diagram that shows you the order of the energies of these orbitals. I don't really like to worry about looking at that because the periodic table tells us what's higher in energy, what's lower in energy. So, and we'll get to that in a minute. So the ground state of an atom. Okay, so an atom at its lowest energy state, the lowest energy configuration, because an atom can be in an excited state. If we put it at a really high temperature, give it a lot of energy, the electrons start popping up into higher energy orbitals and so forth. So there are infinite number of excited states, but there's only one lowest energy state. And basically what that means, we use the Aufbau principle, which would be, in other words, it's a simple way of just saying that the electrons are going to fill the lowest energy orbitals first. So let's start with our first 3, and then we have a kind of carbon here. First 3 atoms on the periodic table. So hydrogen has 1 electron. So 1 electron, the lowest energy orbital is 1s, so it's going to go into the 1s. We write it as 1s1. You will also sometimes see like a box with this 1s below it, and we can put our spin up or our spin down to represent our 1s1. Sometimes, and actually most of the time, I don't write the whole box. I just write a line. I say this is 1s, and then I'll put my 1 electron there. And that's one way to represent it. That tells you how the spin is as well. Then we go up to helium. Helium, we add another electron. So it's going to go into the next highest orbital, but the next highest orbital is still 1s because that 1s orbital can take 2 electrons, right? So we would put in that, we would just add a second, except now it's going to be spin down, or if we were to write it here, it'd be spin down and spin up. So we have pairs of electrons. That way, each of those electrons does not have the same set of 4 quantum numbers, okay? Now we go from, once we've got helium, we add a 3rd electron and we get lithium, right? The thing that's powering all these batteries that we're paying attention to this with. And so the first 2 electrons go into 1s, right? And if all other things being equal, if each orbital could take multiple electrons, we would put the third electron in 1s because that is the lowest energy orbital by far. But because we can only have two orbitals, right? So we have this 1s, can't be 1s3 because we can only have two electrons per orbital. So the next highest orbital, if we went back to our previous slide, is the 2s, not the 2p, it's the 2s. And so we put 1 in there. And so we would write that if we had the boxes, we would put our two paired electrons in the 1s. And then it doesn't matter, we can write spin up or spin down. If I wrote them this way, they would be this way. Let's write that one spin down, doesn't really matter, same energy. So that would be our electronic configuration of lithium. And we would go on and on. So let's do carbon. Now, carbon has 6 electrons. So the first two, we're going to put in the 1s. All right, we know that. Then we know from our lithium, we know that 2s is our next highest, and it can take 2. That's 4 of our electrons. We still got 2 electrons left. What was next on the list? Well, n equals 2 still has 1 more orbital, so it's 2p, and we will put 2. Okay, because remember, the p orbitals can take 6 electrons. Now, if we were to write, and I'm going to write the boxes, but I'm going to write these little lines. So we got 1s, 2s, and then 2p has 3. So we're going to put our 2 electrons in there, spin up and spin down. Our 2 electrons in the 2s, spin up and spin down. Now we've got 2 electrons that go into the p. And so I'm going to put 1 in, spin up. Now we don't pair it. Okay, now this doesn't tell us whether things are paired. We don't put it in this orbital, we put it in this orbital. Okay, so we fill each orbital first, or actually I should say half fill each orbital first. And then once we get to, so we would put 1, if we had the third electron, so if we were in nitrogen, for example, there would be a third electron. It would go in this other, it would go here. But then we go to oxygen where it has the 4th electron. Then we have to start pairing in the 2p. Okay, but that's how you write the electronic configuration, and that's how you write these electronic configuration diagrams that show kind of spin. All right. But as I said previously, we don't want to memorize the order. It was easy enough with carbon. We only had 6 electrons. We had to know 3 orbitals in their order. So what we're going to do is we're going to use the periodic table. Now we're going to ignore the first because this is 1s1 and 1s2, and they're kind of out of place. The helium is out of place comparatively. But if we look at the organization of the periodic table, see this little area here are the NS. This whole block here is the ND. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So whatever column it's in would be whatever superscript you would put. If we're looking at zinc, it would be a D10, right? Anything in this column here would be D10. And that's how you read the periodic table. So S1, S2, and then the Ds, and then this block here in this part, and this is the reason why helium doesn't fit, is the NP. And we have 1, 2, 3, 4, 5, 6. So we can have 6, and just look where it is on the periodic table, what column it's in on the periodic table, and it tells you how many p electrons it has, how many d electrons it has, how many s electrons it has in that particular electronic configuration. Oh, and the last one is these are the NFs down at the bottom. We don't even put them in. They actually go where the purple is, which would make the periodic table kind of expand in a lot of gaps. But that's basically, so if you just look at the periodic table and you count what position it's in and what electrons came before it, you'll know its electronic configuration, okay? So let's go to the next one. And actually, I want to go back a second. So this far right column, I did want to mention this because helium goes in this far right column. The one thing about this is we are in an NP6 at this end. Each one of these is completely filled, right? So it may have had it may have had s electrons, but it has 2 already. It may have had d electrons, but it has 10 already, and it may have p electrons, but it has 6 already. So this column of the inert gas elements is completely filled with an NP6, and that's going to be kind of special to how we write our electronic configurations. All right, so we have our completely filled shell. So if we go back to magnesium, and the magnesium is right here. It has 12 electrons. Okay, so if we were to look at that, it's in the NS2 position. Okay, it's going 1, 2, 3, so this is third down. So those are 3s at that point. But we have all the other 10 electrons. Oops, sorry. And so if we look at that, we have 12 electrons. And so we got 2 in the 1s, 2 in the 2s, then 6 in the 2p. That's 10 of the electrons. And then we have 2 more electrons, and they go in the 3s2. Now you'll notice something about that all the way up to the 2p6. So that's the 1s, 2s, 2p6. Notice that's the same configuration as neon. And so, like I said here, this is equivalent to the neon configuration. So it's actually simpler. We don't really need to write all these 1s2, 2s2, 2p6 because they're just they're completely filled shell. And they're actually what we call core electrons. They don't participate in much of chemistry. So we're really only interested in the last row electrons, the valence electrons. So we're going to represent all of the core electrons with this shortcut, which is the symbol of the completely filled shell of the row right above the row that magnesium is in. Okay, and then it has 2 valence electrons, and they are 3s2. So we could do the same thing for chlorine. Let's go back and find chlorine. Chlorine has 17 electrons, so it's 17 electrons. And let's find it's right above it is neon, so it's on the same row as our magnesium. So it has neon, and that represents 10 of the electrons. And then there are 3s2, and then there were no d's. If you notice, there's a gap here in the d's. There's no d's between it. And then it's 1, 2, 3, 4, 5 p electrons, so 3p5. So neon, 3s2, 3p5 would be the ground state electronic configuration of chlorine. Now, there turns out if you follow that rule and you just count the columns on the periodic table, you're going to get 99% of them correct. But there are a couple of exceptions that aren't really all that important, except if you want to get the configuration correct. And it turns out that there's a benefit to being half-filled and completely filled. And so there's a reason why that last column is inert, that once it's completely filled, it doesn't like to do any chemistry. And so half-filled and completely filled, if we were to go back and we see chromium, and actually I have to go back 2 of them, right? Chromium's right here. And if we were to assign it, we'd have 2 s electrons and then 4. It's in the 4th column of the d electrons, right? And so that's what I put down here. If we went by location, that would be its position, 4s2, 3d4. Well, it turns out there is a benefit to a half-filled d shell. So we take one of these and we pop it into the d, and so its ground state configuration is actually 4s1, 3d5, where we have, and then the reason why this half-filled is energetically favorable is that we have all these unpaired electrons, each in its own individual orbital. We don't have to put any electrons together. And so that is the ground state configuration of chromium. And actually, if you look down that column, you would almost predict that each one of the other two in the each one of the others in that column would do the same thing. So we look at copper. Let's go back. Oops, sorry, wrong way. And we go to copper. Copper is right here. That should be 4s2, 3d9, right? If we looked by the location, 4s2, 3d9. But remember, completely filled, so we're going to pop one of those electrons up, and so it's not going to be that. It would be actually, so we need to put the core electrons in there. The argon, 4s1, 3d10. And that's its ground state configuration. And those are pretty much your exceptions. Those two columns in the half-filled at the D4 and the D9, they can potentially pop an extra electron up into the d orbital to make it half-filled and completely filled. So this is our kind of summary. We fill up electrons in an atom by the Aufbau principle. We should be able to use the periodic table. So at this point, you should be able to assign the ground state electronic configuration of any atom in the table, especially considering that you have a couple of exceptions you just have to know. Those are the half and completely filled D shells. So until next time.